Hello learners, welcome to Unfold You, your favorite digital learning platform. I am Andeep, your mathematics mentor. Today's topic is real numbers. In this video lesson, we are going to study about Euclid's division lemma and its application. So let's get started. See, we are already using four fundamental operations of addition, subtraction, multiplication, division of integers. Now I am going to discuss a very important property of integers, which is Euclid's division lemma. But before that, let us recall what is long division process. In the long division process, when a greater number is divided by a smaller number, we get some quotient and some remainder. Say for example, I divide 13 by 3. So I get quotient as 4 and remainder as 1. In this process, we used to write this as dividend is equal to divisor into quotient plus remainder, where remainder is greater than equal to 0 and less than divisor. So from this we get 13 is equal to 3 into 4 plus 1. Now let's see what is the statement of Euclid's division lemma and what is the similarity between Euclid's division lemma and this long division process. Before that, you must remember this statement. This is very important, so just keep it in your mind. Now let's see what is the statement of Euclid's division lemma. It states that let a and b be any positive integers. Then there exist the unique integers q and r such that a is equal to bq plus r and r is greater than equal to 0 and less than b. Now if I compare this with the statement of long division process, what do I find? That Euclid's division lemma is nothing but just a restatement of long division process, where this q and r, they become the quotient and remainder when the greater number a is divided by a smaller number b. So now if b divides a completely, we write this like using this symbol. This is read as b divides a. Then the remainder in that case will be 0. And if b does not divide a, then we get some remainder and the value of that remainder lies between 0 and b. Now next we are given integers from 1 to 50. Now suppose we want to write these integers in the form of multiples of 2 or multiples of 3. How we can do that? Let's find out. Let's first find the multiples of 2. The multiples of 2 are 2, 4, 6, 8, 10 and so on. Now all these multiples of 2 we can write like in the form of 2n, where n is any integer. Same way we can write 4, 6, 8 and so on. Now let's see the numbers which are greater than 2 and which are not multiple of 2. Such numbers are 3, 5, 7, 9 and so on. Now if I take any two consecutive numbers, say for example I take 4 and 5. What is the difference between them? The difference is 1. Same way if I take 8 and 9. What is the difference? Difference is 1. So we find out that the difference between the numbers which are multiple of 2 and which are not multiple of 2 is 1. So we write these numbers as 2n plus 1. Same way we can write 5 as 2n plus 1. Same way 7 and so on. So we find out that the integers can be written in the form 2n or 2n plus 1. Now when the integer is of this form 2n, it is a multiple of 2, so it becomes an even number. And when integer is of the form 2n plus 1, it becomes an odd number. Same way we can check it for the multiples of 3. Now the multiples of 3 are 3, 6, 9. Now I can write the multiples of 3 as 3 into n, where n is any integer. Now let us take the numbers which are greater than 3 and which are not multiples of 3. Such numbers are 4, 5, 7, 8 and so on. So let me take this 3 and 4. What is the difference between them? The difference is 1. So I can write 4 as 3n plus 1. Now if I take the numbers 3 and 5, what is the difference? Difference is 2. So I can write 5 as 3n plus 2. Same way 7 I can write 3n plus 1. 8 I can write 3n plus 2. So what do we find out? That all the integers, they can be written in the form 3n, 3n plus 1, 3n plus 2 if we are talking in the multiples of 3. So ये जो अभी हमने study किया from this table, how to write this, how to prove this using Euclid's division lemma, let's find out. Now the next we have is example 1, which is show that every positive even integer is of the form 2q and every positive odd integer is of the form 2q plus 1 for any integer q. So for this, the first step is let a be any positive integer. And what will be the value of b? The value of b will be 2. Why? Because we want to express a in the form of 2q or 2q plus 1. So we have let a be any positive integer and b is 2. So when I apply Euclid's division lemma to the integers a and b, what do I get? We get a is equal to 2q plus r, where r is greater than equal to 0 and less than 2. And this q and r, they are integers. Now what are the possible values of r? R is an integer and it is lying between 0 and 2. So the possible values of r will be 0 and 1. Now let us put this values of r one by one in this equation to find the values of a. So when r is equal to 0, we get a is equal to 2q. And when r is equal to 1, we get a is equal to 2q plus 1. So we see that when a is equal to 2q, it becomes the multiple of 2. So in that case, it is an even integer. And when a is equal to 2q plus 1, then a becomes an odd integer. Example 2, which is show that any positive integer is of the form 3q or 3q plus 1 for some integer q. Now here the first step is same. We'll take a be any positive integer. And what is the value of b now? B will take that is equal to 3. Why? Because we want to express a in the form of 3q or 3q plus 1 or 3q plus 2. So we write let a be any positive integer and b is equal to 3. Now if I apply Euclid's division lemma to the integers a and 3, what do we get? We get a is equal to 3q plus r, where r is greater than equal to 0 and less than 3. Both q and r are integers. Now what are the possible values of r? R is an integer and it is greater than equal to 0 and less than 3. So the possible values of r will be 0, 1 and 2. Now we'll put these values in a to find the value of a. So when r is equal to 0, we get a is equal to 3q. When r is equal to 1, we get a is equal to 3q plus 1. And when r is equal to 2, we get a is equal to 3q plus 2. So we write that any positive integer is of the form 3q or 3q plus 1 or 3q plus 2. Example 3, which is prove that if x and y are odd positive integers, then x square plus y square is even but not divisible by 4. Now we know that any odd positive integer is of the form 2q plus 1, where q is any integer. So we take x is equal to 2m plus 1 and y is equal to 2n plus 1, where m and n are integers. Now we want the value of x square plus y square. So just put the values of x and y in this. We get 2m plus 1 whole square plus 2n plus 1 whole square. Now we apply the identity a plus b whole square, which is equal to a square plus b square plus 2ab. And same way for 2n plus 1 whole square, we get 2n whole square plus 1 whole square plus 2 into 2n into 1. So solving this, we get 4m square plus 1 plus 4m plus 4n square plus 1 plus 4n. Now you can combine the terms of 4 and then you can take 4 common and we are left with 4 into m square plus n square plus m plus n. You can put this term to be equal to q. So finally we get x square plus y square is equal to 4q plus 2. So here we see that as 4q is a multiple of 2, so it is even, 2 is also even. So this 4q plus 2, which is equal to x square plus y square, this is an even number. Now when we divide x square plus y square with 4, this is what we are getting as a remainder. So remainder is 2. So as the remainder is not equal to 0, so we write that it leaves remainder 2 when divided by 4. So finally we have that x square plus y square is even and leaves remainder 2 when it is divided by 4. Hence we solve this question. So moving to the next one, we have example 4, which is use Euclid's division lemma to show that cube of any positive integer is either of the form 9m, 9m plus 1 or 9m plus 2 for some integer m. So first we take x to be any positive integer. So we already did in the previous examples that if x is any positive integer, then it is of the form 3q, 3q plus 1 or 3q plus 2. Now we take the values of x one by one and solve it for x cube. So when x is equal to 3q, what is x cube? X cube will be 3q whole cube. So we get 27q cube. Now we want to write it as a multiple of 9. So I'll take 9 common here. So we are left inside with 3q cube. So you can put this to be m. So finally we write that x cube is equal to 9m, where m you can write this is equal to 3q cube. So next, if we take the value of x is equal to 3q plus 1, what do we get? X cube will be equal to 3q plus 1 whole cube. Now we apply the formula a plus b whole cube here. So this is equal to a cube plus 3a square b plus 3ab square plus b cube. So solving this we get 27q cube plus again here 27q square plus 9q plus 1. So from the first 3 terms we can take 9q common. So we are left with 3q square plus 3q plus 1 and then plus 1. Now you can put this to be equal to m. So finally we get 9m plus 1. So in this case we are getting that x cube is of the form 9m plus 1, where m is q into 3q square plus 3q plus 1. Now let's see what is the value of x cube when x is equal to 3q plus 2. So when x is equal to 3q plus 2, x cube will be 3q plus 2 whole cube. Now here again we apply the formula a plus b whole cube, which is equal to a cube plus 3a square b plus 3ab square plus b cube. So solving this we get 27q cube plus again we get here 27 into 2 is 54. So we get here 54 q square plus 36q plus 8. So again from the first three terms we can take 9q common. So we get 3q square plus 6q plus 4 plus 8. So we can put this equal to 1 is equal to m. So finally we get x cube is equal to 9m plus 8. So in all the cases we found that x cube is either of the form 9m, 9m plus 1 or 9m plus 8. Now next we have is highest common factor, which is HCF. So the HCF of the two positive integers, say a and b, is the highest positive integer that divides both a and b. For example, if we take 24 and 42, the common divisors of 24 and 42 are 1, 2, 3 and 6. So the largest among these is 6. So we write that 6 is the highest common factor, or we say greatest common divisor of 24 and 42. And one thing more, that HCF of two or more positive integer always exists and it is unique. Now let's see how we can find the HCF of two numbers using Euclid's division lemma. Let's find out. Now suppose we have to calculate the HCF of two numbers, say 455 and 42. So for that, if we divide 455 with 42, what do we get? We get quotient as 10 and remainder comes out to be 35. So same thing if we write using Euclid's division lemma, we write that 455 is equal to 42 into 10 plus remainder, which is 35. Now see, if remainder comes out to be 0, then the divisor at that step becomes the HCF of the two given numbers. Now here the remainder is 35, which is not equal to 0. So अब क्या करेंगे? We take this divisor to be our new dividend and this remainder to be our new divisor. So we again divide 42 with 35. So what do we get? 1 is the quotient and the remainder we get is 7. So again using the Euclid's division lemma, we can write that 42 is equal to 35 into 1 plus 7. Now again the remainder is not equal to 0. So this 35 becomes the new dividend and 7 becomes the new divisor. So we divide 35 with 7. So at this time we get remainder to be 0. So using Euclid's division lemma, we write this like 35 is equal to 7 into 5 plus 0. Now as the remainder is 0 in this case, so in this case whatever is the divisor, that is the HCF of the given numbers. So the divisor here is 7. So we write that 7 is the HCF of 455 and 42. Now next example is, if D is the HCF of 56 and 72, find X and Y which satisfies this equation and also prove that X and Y can have more than one value. Now if I apply Euclid's division lemma to integers 56 and 72, what do I get? That 72 is equal to 56 into 1 plus 16. Let it be 1. Now since the remainder is 16, it is not equal to 0. So again we apply Euclid's division lemma to 56 and 16. So what do we get? That 56 is equal to 16 into 3 plus 8. Again the remainder is not equal to 0. So we apply the Euclid's division lemma again to the numbers 16 and 8. So finally we get 16 is equal to 8 into 2 plus 0. So the remainder here is 0. So at this step, whatever is the divisor, that becomes the HCF of the given numbers. So divisor here is 8. So we write that the HCF of 56 and 72 is 8. Now we want to express this 8 in the form of 56x plus 72y. So for that, we find the value of 8 from this equation. We get 8 is equal to 56 minus 16 into 3. And now we put the value of 16 in this equation from the first one. So from first we have 16 is equal to 72 minus 56 plus 56 into 1. So when I put the value of 16 in this equation, what do I get? Let's see. We get 8 is equal to this. Now solving this equation, just open the brackets and solve it. So we get 56 minus 72 into 3 plus 56 into 3. Now combining this and this term, we get 56 into 4, and this is written as minus 3 into 72. Now if we compare this equation with 56x plus 72y, what do we get? The value of x is equal to 4 and the value of y is equal to minus 3. Now we want to prove that x and y can have some other values also. So for this, we add and subtract the product of the given numbers, which is 56 into 72. So we subtract this and we add this also. So combining this term with this term, we get 56 is common. So inside we are left with 4 minus 72. And combining this and this term, here 72 is common. So we can take it out. So inside we are left with minus 3 plus 56 into 72. So solving this, we get 56 into minus 68 plus 53 into 72. So this is equal to 8. Now if we compare this equation again with this, what are the values of x and y now? X we get is minus 68 and y is 53. Now see, we are getting different values of x and y. Initially it was x was 4, y is minus 3. Now we are getting x is equal to minus 68 and y is equal to 53. So we find out that x and y can have some other values also. They are not unique. Determine the largest number that will divide 398, 436 and 542, leaving the remainder 7, 11 and 15. Now when we are dividing the given numbers with the required numbers, we are getting remainder 7, 11 and 15. So it means that when we subtract 7 from the first number, we get 391. Same way, if we subtract 11 from 436, we get 425. And same way, if we subtract 15 from 542, we get 527. All these numbers, after we subtracting the remainders, all these numbers, they will be exactly divisible by the required number. So it means we have to find the highest common factor of all these three. So let's find out. So finding the HCF of the first two numbers 391 and 425 using the Euclid's division lemma, we have that 17 comes out to be the HCF of these two numbers. Now let's find out the HCF of 527 and 17 using same Euclid's division lemma. So we find out that the HCF is 17 and 527 is 17. Why? Because the remainder at this step is 0, so the divisors comes out to be the HCF. So we find that HCF of all the three numbers is 17. So the required number comes out to be 17. Now the next example is, a sweet seller has 420 Kaju Burfis and 130 Badam Burfis. Now she wants to stack them in such a way that each stock has the same number and they take up the least area of the tray. So we need to find out what is the maximum number of burfis that can be placed in each stock for this purpose. Now in some questions we get confused what we need to find out, whether we need to find out the HCF or we need to find out the LCM. So for this you need to remember that whenever the question is that we have to arrange something into rows or groups, we need to find out the HCF in that case. So here also we need to arrange the burfis in the tray so that they take up the least area of the tray. So we find out the HCF of the two numbers, which is 420 and 130. So let's find out the HCF using the Euclid's division lemma. So using the Euclid's division lemma, we find out that 10 is the HCF of the given numbers, which is 42 and 130. So we find that the sweet seller can make stacks of 10 for both the kinds of burfis. Now next example is, there are books on three subjects, namely physics, chemistry and mathematics, which have to be stacked such that all the books are kept topic wise and the height of each stack is same. Total number of the books are also given. Total number of physics books is 96, chemistry is 240, mathematics is 336. Considering the thickness of the books to be same, we need to calculate the number of the stacks of physics, chemistry and mathematics books. See, in this case also we need to arrange the books. So we'll find out HCF of all the three numbers, which is 96, 240 and 336. So using the Euclid's division lemma, we again find out the HCF of the three numbers. So we find out that HCF comes out to be 48. So therefore 48 books must be there in each stack. Now let's find out how many numbers of stacks are there for each subject. So the number of stacks for the physics books will be total number of physics books divided by number of books in each stack. So we divide both. So the total number of physics books are 96 and the number of books in each stack is 48. So we get the number of stacks for the physics books will be 2. Same way we can find out the number of stacks for the chemistry books, which is equal to 240 by 48, which is equal to 5, and same way the number of stacks for mathematics books will be 336 divided by 48, which is 7. Just note all the problems and try to solve it yourself. Solutions are also mentioned for third and fourth, and in case you are having any doubts, you can clarify all your doubts using Ask Your Doubts section at Unfold You. So this was all for today's topic. See you again in the next video with the new topics. Till then, keep learning, keep sharing. Thank you.